looked at moment of inertia for different shapes when the axis passes through the center of mass of the object, but that doesn't have to be the case. This is going to be a video about parallel axis theorem. The idea here is this. If I've got my favorite disk that I keep using over and over again, if I've got my favorite disk, I can put an axis right through the center of the disk, and I will spin about that axis, and we know how to handle that. Disk has a mass m and a radius r. This one is going to be a central axis that passes through the center of mass of the wheel. But what if instead I wanted to rotate this about some other axis? What if I wanted to rotate about here? And we're going to say that the distance from here to my center of mass is going to be some distance d. This is a shifted axis. It is a parallel axis because it's parallel to the axis that passes right through the middle, so that's where the name of this thing comes from. Now, an immediate question that is definitely worth asking is why? Why would I do this at all? And there are different answers to that. One, sometimes you just aren't rotating around the center of mass. Now, if I take this thing around the shifted axis and I spin it, right, if I have a wheel like this, and I try rotating it about this axis, it can do that. Like, that's okay, it can handle it, but that's going to wobble. This is actually exactly how you make vibrating functions in electronics. So if you have, the vibrate mode for your phone, or if you have a video game controller, it'll have these asymmetric disks, or the disk will be symmetric about an asymmetric axis. Now, this particular way of doing this, that's less helpful, because that is kind of messy as that spins around. So in practice, what this looks like a lot of the time is, for like game controllers and such, is to just start with a wheel, have it go about a central axis, but then remove part of the wheel. If you can remove part of the wheel, then the whole thing wobbles anyway. And the more of this that you remove, right, if I remove this part of the wheel, I don't think I can erase it. If I remove that part of the wheel, then I'm left with something that's going to be asymmetric. If I remove a bigger part of the wheel, then it's going to be more of a wobble. If I make this thing heavier, that's going to be more of a wobble still, and a lot of times the way that I make this heavier is by just increasing the size of the cylinder. I told you that the height of the cylinder doesn't actually factor in, and it doesn't except in the context that a heavier cylinder or a taller cylinder will be heavier. So if you are going to make this out of one material, the way that you make this heavier is by just making your cylinder taller. Back to parallel axis theorem. The moment of inertia about the central axis, in this case about the center of mass, is going to be, this is a solid cylinder, so it's going to be half mr squared. If I want to work with a shifted axis, the moment of inertia about that axis, shifted axis, is going to be the moment of inertia about the center of mass plus m times d squared. And that's really it. It's not more complicated than that. I want to show you how this works with an example that you already know. When I had a bar that had the axis passing through the center of mass, through the center of the bar. This bar had a mass of m and a length of L. And when I did that, I got a center of mass moment of inertia of 1/12 m L squared. So what happens if I shift this bar, if I shift the axis to the end? Well, the distance between this and the center is just L over 2 now. So let's figure this out. The moment of inertia about that shifted axis is going to be the moment of inertia about the center of mass plus m times d squared. D is L over 2, so I'm going to get my 1/12 mL squared, that's from center of mass, plus m times L over 2 squared. Keep this front term. If I expand this one out, I'm going to get L squared, and half squared is 1/4. Now I can common denominator this thing. So let's do that. I'm going to 12ths, so I would like to take this 1/4 and put it into 12ths. I'm going to multiply by 3 over 3. That gives me 1/12 mL squared plus 3/12 mL squared, or 4/12 mL squared. 4/12 reduces to 1/3, and I get 1/3 mL squared, which is what I know the moment of inertia is for a bar about the end. If I'm doing a problem with a bar about the end, I'm just going to use that 1/3 right from the start because I already know that value. But this was just a way of using a known commodity to be able to get to an endpoint and show you kind of how this works in practice.